Road-weary travelers, it's time to find our way home on our road map. This is a legit road map. Starting in one place, going everywhere. Start here with this alcohol. Okay. How do I make that alcohol into this? Sorry, this, did I say this is an alcohol? That's weird. That's an alkene. How do I make that alkene into this Markovnikov alcohol? That is an early reaction, and yes, these always have review on them, without exception. Yes, all of our old stuff to make our new stuff so we can use it is all relevant. So do you remember the reaction in 6.1b? That H2SO4 is the cat, and H2O is the reactant. Yeah. We're skipping this because I told you to skip. This is winter 23. Skip PCC and other chromium reactions. Yes, one of the C's in there is chromium. I may be adding to this list on this page, but right now we're at that, okay? That was in the study guide to do that, right? Skip PCC. So I'm scratching it out. Okay? But that doesn't mean you're skipping this, right? We know how to make an alkene from an alcohol. That was the very last, second last reaction we did. We did dehydration of normal alcohols, and then we did dehydration of vicinal diols. And those are the last two reactions on your test. And they both had the same reactants. You got to protonate it to make a better leaving group. That's H2SO4. And it's an endothermic reaction that generally requires quite a bit of heat. You got to have the heat in this one. And like I said, any reaction that makes alcohols is a critical review reaction, right? So we had that one already. This one makes an anti-Markovnikov alcohol. We have to know that. And that's just putting the OH on the less substituted O here. The less substituted carbon. Sorry, I said O. And that would look like this. Anti-Markovnikov alcohol. And you're going to get a 50-50 RS mixture. So the product on the left at the bottom is the R. So you get 50% S, 50% R that react with PBr3. There's an SN2 in that, and the S would become that one, and the R would become that one. You don't need those funky arrows. I just need the PBr3. Okay? Just going to remind you, this is now S, and this PBr3 reaction has an SN2 happen on the carbon. It does. So R became S, and S became R, but really you didn't need that. You just need what's the reaction that gets rid of OH and puts a Br in its place. Please don't think about HBr. If you put HBr, I'll tell you what you get. Here it is. It's a new question all of a sudden. I'll put it in an unobtrusive gray arrow, and I'll just say HBr. I don't think you can read that very well. And here's your result. You're going to love it. Maybe not. What happened? How'd the Br end up there? Not here. You protonated this thing with HBr. Then it made a secondary cation. Then it rearranged to a more stable tertiary carbocation. The Br minus went there. So if you thought HBr was the answer here, you're not getting points. End of story. What else? Now it's all about analysis. Look, secondary Rx. Making another secondary Rx, but S became R. Have you memorized your strong nucleophiles yet? No. Nice honest answer there from one of our better students. He's doing it today. He's not putting it off anymore. I minus is on the list of strong nucleophiles. It is. And you want to really make sure it's an SN2 reaction, right? Because I want R to become, or S to become R. Give me a solvent that it really helps the SN2 reaction. You don't get points for it here, but I might consider a half-point bonus. I might consider it. Because you're like DMSO, I consider giving a half-point bonus there because you're making sure the SN2 happens. Now, if you need another SN2 on this page somewhere else, and you keep using the same solvent, you only got the bonus for the first one. But if there are 4 of these type questions where you need an SN2 reaction, and you've picked one of the 4 solvents already, use the other solvent for another half-point bonus. If I'm feeling generous, I'll be giving the half-point bonuses for solvents on these. Okay? I gotta see the I minus. That's for sure. Solvents like a potential bonus there. Okay. Now let's just go until we hit a dead end. I think our first dead end's here. KOET. I want to remind you the pKb of that's less than 0. Less than 0, and this combination, pKb less than 0, heat, what you got? E2. All products are C6H12. Oh. I bet the best one looks like this. Second best one looks like this. What's the difference? I think you're ahead of me. There, the difference is cis and trans between the last 2. I just needed to hear alpha versus beta. Alpha is the carbon with the leaving group. Beta is one away. Beta on the left gives this result. These 2 results. And beta on the right gives that result, which is major. You weren't even asked for major here, so. Why major? And not the other 2? Well, it's got 3 carbons attached to the alkene. We call that a tri-substituted alkene. It has more hyperconjugation, this one, than these 2, which are di-substituted alkene. They only have 2 carbon groups. Now, if you had to choose between these 2, which one would you like a little better? First one has less steric hindrance because it's anti or trans in this case. These groups are bumping into each other almost. That's not good, is it? Okay, that's a lot. Let's go back to a start here and go in another direction. Hey, chromium reactions we're scribbling out. See, CrO3, PCC. And that's good. They were dead ends anyway, right? So we're not losing a lot of this page. How do you make, oh, this is the anti-Markovnikov alcohol again. The chemicals are already on the screen somewhere. BH3 step 1, yeah. What's step 2? Peroxide, hydrogen peroxide, and KOH is good. You're just making a slightly different anti-Markovnikov alcohol. That one versus this one. They came from different alkenes, didn't they? Oh. Yeah, I'm pretty sure you're going to have to draw some version of TS. Okay, I'm not pretty sure. I'm 100% sure on this test, you're going to have to draw some version of TS. Toluene sulfonyl. In this case, that's toluene sulfonyl chloride, and the Cl is the leaving group. This O takes its place, and the pyridine grabs that H. So copy everything here, except for the H on the O. O, CH2, C with a C, H3. New group, sulfur. How many double bonds to O does it have? Remember, sulfonic acids have the same Lewis structure as sulfuric acid, pretty much. And sulfuric has two sulfonyls. Sulfonyl number 1, sulfonyl number 2. It's like carbonyl, isn't it? And then it's got a phenyl. But you got to make that into a toluene by adding a methyl as far away as possible. There you go. You had to draw that out because it's got pi bonds in it. You couldn't use a short form. What can you do? And then we got to make that into that. Oh, 2 points. Are there new carbons in this molecule that weren't in this molecule? Yeah. I think the new carbons, if you think about it, the old carbons, you want them in blue? Old carbons are in blue. I got them in blue up there. This is a new group. This is a primary RX. Some of you are not used to thinking of toluene sulfonate esters. Toluene sulfonate esters are just carbons with a good leaving group, because toluene sulfonic acid, pKa -5, toluene sulfonate, good leaving group. You want to see it? Here it is, plus OTS negative. Good leaving group, not worth any points. And that would give you the new bond. Okay? But it doesn't give you a bromine. And I want my bonus points, so I'm going to write comma DMF. What kind of reaction is that? Strong nucleophile. Primary carbon with leaving group. Polar A product solvent. Everything there said SN2. When she comes back, make sure I take attendance. Don't do it while she's gone, that's mean. Okay, so remember, we've got a toluene sulfonate ester, which is a great leaving group on a primary carbon, and I got a strong nucleophile. That's a acetylide from chapter 7. Remember we did synthesis in chapter 7? And this is the synthesis. There's a carbon with a leaving group. And then DMF is another polar A product solvent. I might give a half-point bonus. Well, and then step 2, make sure you separate these two. Step 2, I'm going to use Br2 and heat. What's that going to do on the tertiary carbon? Tertiary carbons make nice radicals. That's a chapter 7 reaction. I know it's a review reaction. And a really astute student, if they wrote a comment and said, well, if you made this product, it would be minor. Oh, that student would make me very happy, because this carbon here is secondary. And it looks a lot like allylic, right? It's one away from an alkyne, which is like being one away from an alkene, and it can resonate. So the bromine there would be major. If I ever got that comment on a student, I don't know, I'd nominate them for best student of the century because that's really subtle. All right, and there you go. What's going on here? Wow, wow, wow. Huh. You know what would be better? So that wouldn't be the minor product. What happens if I put the BR on this one first? It doesn't have a triple bond there, does it? There's no allylic-like position. All I'm trying to say now is, if I just reverse the order here, I don't have to worry about major and minor. And the truth is, I'll take either order from anybody in this class. What I just did didn't change your points. It just got rid of that major minor issue. And if I can start an SN1 reaction down here, that's carbocations, right? It can rearrange to a more stable secondary allylic carbocation, which is what happened. So I would go something like H2S and HOET. That is a weird looking E, isn't it? H2S, HOET. This is your moderate nu, mod nu, and this is your polar protic solvent. So you can make a nice cation with that. Cation rearranges to a secondary allylic, and then the nucleophile hits that. So yeah. And here's like a mess. There's more products here. Oh, how about this product? You tell me how this product arose. That's the SN1 without rearrangement. Minor. Oh, it says minor. Yeah. What can I do for the other two minor products? Every time you have an SN1 reaction, there's also a minor blank reaction. E1, what new functionality do you have for E1? Pi. So instead of the sulfur ending up there, you get pi either, I haven't drawn it yet, here for major, or well, of the two, I like the first one better. Because you can do elimination from this alpha position or the new alpha position, which is right over here. Okay. I don't even like those labels. Okay. Yeah. So far, so good. Save. Why is this one pi bond here? That's a good question. It should have ended up there. Yeah, this is not a legal product. There's no way that was beta ever to any leaving group. You caught me. That's good. That's better. When the bromine's here, you can go that way or that way, and that covers both products. How about that? No more explanation needed. That's how I'm just going to give you alpha and beta 1 and beta 2. And that's beta 1. And that used to be alpha. And that's beta 2. Bad looking beta. Bad beta. So we're going here, and we're doing some stuff down here. Wow. What kind of molecule is KH? It's really H minus, right? What kind of reaction makes H minus into HH? What kind of reaction is that? What kind of reaction is that? Acid base. Here's an acid, you don't know the pKa. There's a periodic table. What's the element above sulfur? Oxygen. If that's an O, what's the functional group here? Alcohol. pKa of alcohols. What is it? 17 or 18. What's the trend on the periodic table when you go down a column and the atoms get bigger and bigger, which means the anions get bigger and bigger, which means they're more stable. It's easier to make a big anion than a small one. The trend is things get more acidic that way. 17 went down. That's all you need to know. H minus has what pKa? 35. This H minus could take the H off of a real alcohol. It doesn't matter that it's not even a real alcohol anymore. This is an acid-base reaction to make an S minus. And when my same student does review his strong nucleophiles, he's going to see S minus on the list, right? Strong nu. That S minus doesn't look very minus. I'm trying to get a minus. It looked cationish. That was terrible. Strong nu. I need a primary Rx because here's the group. Here's the group. Here's the group. Well, that was fun. It's got a leaving group on it. Primary Rx. Want a half-point bonus? You want an SN2? That's my third SN2 solvent I've given you. Yeah, you made sure this SN2 is going to happen. Good job. This next one, straight up review. How do you make an alkyne into an alkene? Say to, oh, she wants to use it. Lindlar's catalyst gets you nothing, but you're on your way. Lindlar's catalyst, and if you want to use his name, you can't misspell it. But the chemicals that put these two new H's on, you haven't given me yet. H2. Don't forget, H2 and Lindlar's catalyst are two separate things. Or she could have gone with the old BH3, CH3CO2H. Or she could have gone with the old sodium, NH3. When it's a terminal alkyne, you don't care which of the three reductions you do. Right? I'd like to point out if you use the Na and NH3, here's your result. Yeah, the new H's are anti, but I can't tell the black H is an H2. I could never tell. Those gave that result. And these two gave this result. See what I'm trying to say? Yeah. And not the dead end there. Markovnikov addition of H and Br. I think that's the answer. We got a new H on this carbon. We got a new Br on the more substitute carbon. That's our first mechanism of the semester. 6.1a. I love doing this to set up the NGP. Because sulfur's a nucleophile, bromine's a leaving group. This is an NGP molecule. This also NGP. We haven't got there yet. What do they have in common, everybody? They got a new. They got a leaving group. They got both. That combination means NGP. If you're like me, I can't predict NGP products unless I actually do the mechanism, because it's not visually obvious sometimes. So I'm doing the mechanism just this one time. You're going to get, in this case, a triangle. You got an IBU. You got a new bond there. Triangle. And this triangle is not like your other triangles. It's not about attacking the carbon that spends more time with a plus charge. That's not true. This is about attacking the carbon that's easier to get to. Remember, NGP, that's always true. Attack the carbon that's easier to get to. They're both secondary. You can't use that as a criteria. But guys, isn't this a pretty bulky group out here? Do you think this is as bulky? That's a methyl, for crying out loud. This is a branched carbon right there. That makes this position more hindered. The less hindered position that the methanol is going to go for. This is the methanol. Is that position. And you're also going to lose H+. It's not a complete mechanism, but the methanol has an H that's got to go. OCH3 ends up on a carbon that has a methyl to the left. Straight up, it has a C that goes to a sulfur that goes to an IBU. The C that went to the sulfur also went to a sec-pentyl group. There's your molecule. Okay. We haven't set up this NGP yet. I think that's the last thing we got to do. We're going from here. What's your analysis here for a secondary carbon with a leaving group, a strong nucleophile, and a polar aprotic solvent? I got a Mabarif with the leaving group. I've got a strong nuke saying SN2, and I have a polar aprotic solvent saying SN2. You better give me an SN2. See top of page 4 for 2. H2 excess PT, top of page 4. We don't have that. Stop share. Share. Ooh, where are you? Screen. I don't think that helped. Stop share. There's screen. We need the post attendee. That's it, I guess. But it's open here. I can't see the top of my screen. That's the problem. I think it's here. Page 4. Top of page 4. H2PT with a C triple bond to N. I think that's the one we need. I'm just going to snip them all. We only need one of them. So that's my comment. My comment for what up there? Oh, they're right here. Put that in a highlighter. Wow, how'd you do that? Purple highlighter. See top of page 4 for 2. And we have a C triple bond to N. So you do your SN2. You want to see the result of part 1, reaction 1 and 2. No, just 1. Your C triple bond to N is right here on a dash. Why is it on a dash? And the H got bumped out to the front. Why did I draw that? That's part 1. Backside attacks. Good. What happens to C triple N in the next step? C gets 2 new H's. N gets 2 new H's. Get rid of both pi, right? CH2, NH2. How's that? Oh, I like it. I like how that worked. Doesn't it look a lot like CH2, NH2, CH2, NH2? It does. They're almost the same. How do I get a chlorine on this tertiary position where there's nothing special there? It's just hydrocarbon. Chapter 7. We did it with bromine earlier. Want to see it? Bromine and heat went for the tertiary position to put a BR. Nothing special on the tertiary position. Nothing special on the, where the heck am I? I'm here. Nothing special on the tertiary position, but with Cl2 and heat, there will be a Cl there. Initiation, propagation, termination. Remember that? It's on this test. Oh, it's an important chapter 8 reaction. And then NGP. I got to do the mechanism. This time it's a square. I'm going to go to star. I need a new color. Why do you do that? Go to star. Here's star. You got your 2 methyls coming down to an N with 2 H's. Goes to a CH2, to a C that goes to there, it's a square. There's star. Your 2 positions to be attacked, your potential positions to be attacked are there and there. I need these guys separate from each other for clarity. Which of the 2 red dots attached to nitrogen is easier to get to? This time it's a much easier answer. This one. This one's got too many carbons on it. That's where you're going to put your new group on this carbon here. Okay? And it's going to be a methyl. It's going to be the same kind of group as before. OCH3. See that? OCH3. So I'm going to copy OCH3 here. Going to make my new bond to that first dot. And it goes straight up to a carbon with an ethyl, straight over to a carbon dimethyl, straight down to an N with 2 H's. Look at that. Looks like nothing like the original skeleton. NGP can do that. Yeah, this page is intimidating, I know. This page is for the students who are getting a lot of organic chemistry. It's a reward, but it's also a challenge even for them. Because it's got everything. It's got the whole test on it. Like every part of every chapter plus review chapters. We got one missing reagent, but I think it's a that one is a chromium reaction. Chromium reaction, which we're going to skip. But we're supposed to be able to do this for sure. Hey, this is how we started our day today, right? Yeah, that was our first. It's almost the same molecule. Let's see if I can not make the same mistake. Where the pi bond is where you get your vicinal diols of the syn variety, right? They're on the same side. And then it's time to do the pinnacle rearrangement. How do I know? Vicinal diol, sulfuric acid, and heat. If you see any alcohol with sulfuric acid and heat, first thought, dehydration. If it's a vicinal diol, it's a special dehydration called a pinnacle rearrangement. And what happens is you gotta entertain one of the OHs leaving, a rearrangement happening to make the cation with the other O, and then make a carbonyl. So I really like the tertiary one leaving to make a cation. I'll show you the story. These are not a final answer story. This is an intermediate. And the last step has the base, the meow base. I'm going to erase most of this, okay? Meow base. I like that. It's going to regenerate the cat. Oops. This did this. This is a lot of things going on here. Rearrange and then eliminate. Got 3 colors of arrows there. Confusing as all get up. All I want to see is the result. We have a pi bond there and the H moved over here. Pi bond here. I don't want that black. I want that black. That blue. Blue. Yeah, I don't need this here, but it's there. There it is. That'd be major because it came from an initial tertiary cation. If you make a cation here initially, what's going to move away from here to there so the cation can be here? You can't say H. There's no H on this carbon. It's got to be a methyl. So you're going to move a methyl there, make cation there, and a ketone there. So here's the story. You got your ketone here, and the methyl moved here, and there was already an ethyl there. There's your 2 products. The first one, what? I'm sorry, say it again. Oh, it might be. 1, 2, 3. Oh, in the main chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4. Oh, the first product. Yeah. Thank you. And then 1, 2, 3, 4, 5. Good. Yeah, I missed a carbon. Would have been better if I drew it down. That's okay. Those are pinnacle rearrangement products. And I think we finally finished the page. That was a mega. Please move this window. I don't even know what that's saying. Stop share.